Hey everyone, today I'm going to be walking us through how to solve a statically indeterminate problem of the torsional variety. So I hope you learn a thing or two, have some fun, and yeah, so the basic premise of our problem is that we have a outside bar here that's shaded, and inside there is another bar, and that's attached to a rigid disc here, which is attached to a third solid bar, and that's attached on either side to a rigid wall. So this should be a problem we're somewhat familiar with. This is just a cross-sectional view. If you look on the end, you can see there's the outside tube, and there's the inside tube. So, alright. And so the problem we're going to be dealing with today is that we're going to apply a torque to this disc. We'll call it T. And we want to know from that torque what the angular displacement of the disc is. And we'll call that phi disc. Phi or phi. I'm going to call it phi, so if that's wrong, don't get mad at me. So as using the right-hand rule, the torque's in that direction, we can see that the displacement's going to be going kind of up into the board like that. And that's what we're going to call positive angular displacement. So, alright, and we know that this is a statically indeterminate problem because the displacement depends on the material properties. So we're going to need more than just statics to solve this problem. Okay, so we'll start out with an analysis of this from a statics viewpoint. So okay, sorry, my camera on my laptop flips the letters around, so I have to write backwards, so I apologize if I mess that up. Anyway, so from statics we know that there's going to be a reaction on either wall, a reaction torque that opposes the applied torque. And so since it opposes it, they're going to be going in the opposite direction. So over here we have a reaction torque of T3. And over here, we're going to consider actually two of them, the reaction from the inside bar, which actually goes in the other direction. We'll call that Ti. And we have a reaction on the outer bar that we'll call To. Okay, and from statics we know that all of these torques must balance for equilibrium. So everything pointing to the right equals everything pointing, the sum of everything pointing to the left. So pretty simple. T applied equals Ti plus To plus T3. And as you can see, that's three unknowns in one equation. So that's statically indeterminate. We're going to need a little bit more information to solve this problem. So as you can see, I've labeled each of the bars according to their torsional stiffness. The inside bar has a stiffness K subscript I. The outer bar has a torsional stiffness K subscript O. And the third bar has a torsional stiffness K subscript 3. So we're going to be using those to figure out how much displacement there is when we apply a torque. So doing that, what we need is force displacement equations which relate how much each of these tubes or bars is going to turn when we apply a torque to it. So, and those are all in the form of the torque is equal to the torsional stiffness times the angular displacement, which makes sense because for a given stiffness, the more torque we apply, the more it's going to rotate. So, also, if we look at each one of these bars individually, and we're going to know that they also have to be in equilibrium. So, since this reaction torque is acting on this inside bar, the internal torque is going to oppose it. So that's going to have an internal torque of Ti. The outer bar is going to have an internal torque of To, and the same thing for bar 3 is going to have an internal torque of T3. So I hope that wasn't too hand wavy. That's just that's statics. So that's how it works. So anyway, and also to define a sign convention for the torques, we're going to say that torque is positive if it results in an angular displacement in the same direction as the overall torque of the disk. So it turns out actually each torque and each angular displacement is going to be positive because that's the way the disk rotates. So again, hopefully that's not too hand wavy, but it only makes sense. You can make up whatever sign convention you want as long as you're consistent. So for the force displacement equations, we have, for the internal bar, we have Ti equals Ki phi. For the outer bar, we have To is Ko phi O, and for the third bar, we have T3 equals K3 phi 3. So as you can see, the internal torque of the inside bar, for example, will be opposing the reaction, and so it's going to rotate that way, which is positive. It's consistent with phi disk. Same with the outer bar. And over here, the internal torque of K3 is going to oppose the reaction, so that's going to be going in the same direction. So as you can see, they're all of these are positive. So we don't really have to worry about signs anymore. That's kind of nice. The last step to tie this all together is the compatibility equations. So we want to see how each of these angular displacements relates to each other. So as you can see, they're all welded or attached to the same solid disk. And what that means is that they all have to be equal. So let's that's not right. Compatibility. Okay. So the compatibility equation is that they're all equal and they're all going in the same direction as the disk. So phi disk is phi I, which is equal to phi O, equal to phi 3. Okay, so now we have everything we need to solve this problem. It's just algebra from here. So we can do that now. No more need for the diagram. So what we can do here is we can plug each one of these torques into the statics equation. So instead of Ti, we'll have Ki, phi, and etc. So that gets us T equals Ki phi plus Ko phi O plus K3 phi 3. Okay? So that's the statics equation combined with the force displacement. So the last step we need is to use this compatibility equation. So, like I mentioned earlier, each one of these displacements is equal. So we can actually call each of them phi disk and factor it out. So we end up with T equals phi disk Ki plus Ko plus K3. Alright, and the last step is that we want to solve for angular displacement of the disk as a function of torque. So we just divide everything by the equivalent torsional stiffness of the entire system, which is the sum of each individual torsional stiffness. Which makes sense. If you make any one of those bars that I had in the diagram stiffer, the displacement's going to be smaller. So these should all be positive. That would match our intuition, and we can go on. So solving for that, we get the displacement of the disk equals the applied torque divided by Ki plus Ko plus K3. And so that's the equation. We just solved the problem using statics, force displacement, and compatibility. So it wasn't that hard. Probably the most difficult part is signs, not getting the signs mixed up. So in this example, we used kind of a clever, magical sign convention. It was legitimate, but you need to think about those, but not too hard. So I hope it didn't just seem like it was I waved my hand and did some alchemy or something, but that's actually, I mean, it was all legitimate science, So that's how you solve, I guess, a statically indeterminate problem. Feel free to leave comments, questions, anything like that. I'll respond because no one watches my videos. So, yeah, I hope you learned a thing or two. Thanks.